I'm your instructor for the subject Computer Organization and Architecture. In this subject, we have started Unit 3, that is Assembly Language Programming. In this unit, we are going to see today the topic that is multiplication. In this topic, we are going to see how 8-bit numbers can be multiplied by using simple instructions you have used in this assembly language. Okay, so let me start with the topic. Before that, let me see how we can do the multiplication operation of two positive numbers which are of 8-bit. Okay, here we have used x to hold multiplicand, y to hold the multiplier, and p to hold the product, or you can say result. We know that whenever if you multiply two 4-bit number, your result will be of 8-bit. Maximum possibility of your result is of 8-bit. If you multiply two 8-bit registers, your result will be of 16-bit. Okay, so that means you will require double capacity to store your number. So here we are using this 4-bit numbers, but using in 8-bit register, or you can say stored at 8-bit location. That means you have used LSB side 4-bit as a 000. Okay, so by this way we have used this two numbers, that is f and b. X is f, that is 11111, and y is 1011, that is b number, or you can say its hex representation will be b. So we are going to multiplying this 0f and 0b number that you have stored at location x and y, and your product is going to be stored at location p. Okay, so for this multiplication you will first require to check the bit of this multiplier. If it is 1, then you have to add this multiplicand. If it is 0, then you have to add 0000. If you multiply any bit with 1, result will be same, that is another bit. If another bit is 1, then result will be 1. Another bit is 0, then your result will be 0. And if you multiply any number with 0, your result will be 0. Okay, so here you have to first check the bit of the multiplier. If it is 1, then you have to multiply this 1 with this whole number and put over here. Then next we will check for this one, but its position is at second position. That means you have to append 1 0 over here. You have to append 1 0 over here, and after then if it is 1, then your result will be same. Multiply by 1, result will be as number you have, that will be like 1 1 1 1, and after 4 times 0. But here 4 zeros we doesn't require to store, because our result will be of 8-bit only, and we have used already 4 bits only for storing your data. Okay, so we have used only 3 zeros over here. After that there is a 0, but we have not represented over here. Okay, after that we have 0. That means if you multiply this number with 0, your result will be 0000. Okay, but this 0 will be shifted version of 2. Okay, that means you have to first append 2 zeros, and then after that 2 zeros your result of is product, that is 000. Okay, after that you have to check for this one. Okay, this one is at third position, or you can say you have to append 3 zeros. Okay, so here we have appended 3 zeros, and after that you have to multiply this 1 with this whole number. Your result will be like 1 1 1 1, and after that 4 ones, 4 zeros will be there. So we will put over here 4 ones and then 4 zeros. But here only 1 0 is shown because all other zeros are 0. Okay, all other numbers are 0. So we have neglected it. After this partial product, you have to do the addition of this 4 numbers. Okay, so we have to add 1 0 0 0, your result will be 1. Then add 1 1, your result will be 0 and carry will be 1. Then add 1 1 and previous carry 1, your result will be 1, carry 1. Then 1 1 0 1 plus previous carry 1, your result will be 0 and carry will be passed over next, and so on. So your after this 4-bit addition, your result will be like 1 0 1 0 0 1 0 1. This is your pen and paper product that we can do, because we can add this 4 bits, 4 ones at a time, because we know if you add 4 ones, your result will be 0 and carry will be 1 0. If you add 3 ones, your result will be 1 and carry will be 1. Okay, but full adder can add only 3 bits. You can't add 4 bits at a time. Okay, so that you have to do this addition by doing partial. Okay, that means if you are considering this partial product, then you have to add this. If you are considering this partial product, then first you have to add this, and after that you have to add this partial product. After this addition, you have to add this partial product at a time. Okay, that means you have to add your partial product into some location which is already clear, and after every partial product you have to add that, so that your full adder can work, because full adder can work only on 3 bits. Okay, so for this we can use this p location, that you have stored 0 0 0 0, and if your multiplier's bit is 1, then add this multiplicand, then check for the second bit, or you can say second position numbers bit. If it is 1, then add the one time shifted version of multiplicand. Okay, if your third bit is 1, then add the two time shifted version of multiplicand to this partial product, or you can say partial sum. Okay, by this way we have to do this multiplication. That means first we have clear, then we will check for this LSB bit of the multiplier. If it is 1, then add the multiplicand. That means we have added this multiplicand. Our result will be like 0 0 0 0 1 1 1 1 1. After this we will have to check for the second bit. If it is 1, then you have to add this shifted version, that is 0 1 1 1 0 0 0. Shifted version to this partial product. You have got this partial product. You have to add this number into this number, and you will get the result like 0 0 1 0 1 1 0 1. Okay. After that you will check for the 0. If it is 0, then you no need to addition. Okay. Then it is as it is. Then check for the next bit. If it is 1, then shift your number. Here, if it is 0, then also you require to shift this multiplicand. Okay, that you have already shifted. That shifting is required for the next time, because here you will require, here for this one you will require 3 times shifted version of x. Okay, but if you have not shifted in previous case where you have 0, okay, so you have to shift this for 2 times, and that you can't pop up. So you will every time you will shift this number. If it is 0, then you will not do addition. If it is 1, you will do the addition. Okay. So after shifting, you have some bit pattern like 0 0 1 1 1 1 0 0 for this 0. Okay. After that you will check for this bit. If it is 1, then add this shifted version. This shifted version will be like 0 1 1 1 1 and 0 0 0 0, and this you will add this into this partial product, and after that your result will be like 1 0 1 0 0 1 0 1. That is same as your previous case, because multiplicand result will be same, but here we have done this by adding partial. Okay, adding partial. So by this way we can do this multiplication operation by using some 2 8-bit numbers, and we have to design this by using instruction. Before that, let me see the flow chart for this all of this task. As if we want to design this by using some instruction, we have to use some memory locations to store this content. Store this multiplicand, multiplier, and this partial product. We have to use memory location. We have represented this by x for storing multiplicand, y for multiplier, p for the partial product. Okay, and we are using here. We have to check this bit, this bit. For this, we will shift this number to the left side. Okay, so that your number that you require to check is available into the carry flag. Okay, if you do circular shifting, then your this LSB bit, circular shift left, then your LSB bit will be available into E flag, and then you can check the E flag, because we have some instruction for checking E flag, whether it is 1 or 0. We have some instruction. Okay, so we will use this shifting left operation with E flag, and we will check the E flag whether it is 1 or 0. Okay, so for all of this bit of this multiplier, we require to check for the 8 bit. We have to check 8 times the E flag. So we will use some counter for this. And for counter, we have instruction ISZ, increment and skip if 0. Okay, so that in that we are checking some memory locations contained. If it is 0, then we are not skipping next instruction. Okay, if it is other than the 0, then we are executing that instruction, and if its content is 0, then we are skipping that instruction, and then in that skipping we will use some branching instruction. Okay, in short, you have to understand over here that we have to use some counter, and that counter should be in negative number, because we are using the increment and skip. After that instruction, your content of that memory location is going to be increment. If you have used 8 as a counter, then your counter will be next time 9, 10, 11, 12 and so on. So that will not be 0 at any time. Okay, so you can't check the condition for your counter that your counter is completed or not. Okay, so for that we will use the counter in terms of minus. We will use counter as a minus 8, and then we will increment it by 1. That means it will be minus 7, minus 6, minus 4, minus 5, minus 3 and so on. It will become 0 at some level, and that 0 indicates that your counter is completed. Okay, so for that we have first used this counter as a minus 8, because we have to check for the 8 bits. Okay, then we will use this partial product term where we are storing our partial product as a 0, 0, 0. Clear that location. Okay, so we have stored 0 at the P location. Then we will do the circular shifting of this Y contained, and we will bring this LSB bit into E flag. But for that we have to first clear the E flag. If it is 0, then okay. If it is 1, then your circular shifting will also change your MSB bit according to your E flag. So that garbage value is not passed into accumulator, we have to clear the E flag first. Okay, so we will first clear the E flag, then store that number Y, store this Y number into accumulator, because the shifting operation can be done only on the content of accumulator. Okay, so first we will clear the E flag so that garbage value cannot pass into accumulator. Then we will store this Y, or you can say multiplier, into accumulator register over here. Then we will do the circular shifting of EAC. That means E bit will be shifted to the MSB, and LSB of the accumulator is going to be shifted into E flag. Okay, so our LSB bit, whatever this our LSB bit is there, that is passed into the E flag. Okay, then we will store this shifted version of Y to the accumulator, so that next time we have to shift only one time. Okay, so that we have to shift only one time for next time. So we will store this accumulator, that is shifted multiplier, to the location Y. Okay, in that case your Y will be like 0, or you can say 1, 0, 0, 0, then 1, 0, 1. Okay, for one time shifting is done. After shifting, you have to check for the E flag, whether your this LSB bit, that is right now it is in E flag, if it is 1 or 0. If it is 0, then you are required to just shift your content. If it is 1, then you will require to add this shifted version of multiplier, or you can say this X. Okay, if it is 1, then you require to add this shifted version. If it is 0, then just require to shift this number. Okay, so here we will, for first case, if it is 1, then we will add this P and X. P is already 0. Okay, and result is going to be stored at location P, and after this we will clear the E flag. If it is 0, then it is already clear, then no required to clear. But if it is 1, then you require to clear it for next time. Okay, after this, whether it is 1 or whether it is 0, you have to shift this X, because after that you will, whenever you will do the addition, you require this shifted version. Okay, so then we will do this shifted of this X location. For that, you have to bring it to the accumulator, then circular shift left ESC, and then store a shifted version to the X location. So that next time you just require to add that. Okay. And this operation will require whether your number is 0 or 1, whether your LSB bit is 0 or 1, shifting is required. Addition will depend on 1. If it is E flag is 1, then you require to add and then shift. If it is 0, then shift only. For the multiplicand bit. For multiplier, we are checking whether it is 1 or 0, and depending upon we will decide this addition is required or not. Okay. After this, we will increment the control or increment the CTR, increment the counter by 1. That means it will be -7 after 1 increment. And lastly, we will check for this if it is 0 or not, if this counter is 0 or not. If it is not 0, then do the second time the same operation second time. First clear the E flag, then put the multiplier into accumulator, then shift it, check for the then store the shifted version to the that location, then check for the carry flag. If it is 1, then add the shifted version that you have already shifted in last case, then add this shifted version of X into partial product. If it is 0, then only shift for the next time, and continue this task up to when your counter is 0. Okay. So after 0, your task is completed, your product is stored at location P. So this will be your flow chart for your multiplication task. Next, we have to convert this flow chart into instruction. By using our total 25 instruction, we have to convert this. For this, we can use like this. Let me see what are the instructions. For first, we have to start with some location. We have used org 100 for starting this. For second, we have to store this X, Y, your multiplicand, multipliers, that is your F and B at X and Y. Here I have given these numbers, but if you don't know at which location that is stored, that is okay. But you have to give some label. Okay. At CTR, that is your counter, we are loading this with 8 number, P with 0, that contains your partial product, and X is your multiplicand, and Y is your multiplier, that is 000F and 000B. Okay, so this is your starting, that is your labels where you have stored your numbers and where you are going to storing your partial product. After this storing, we are going to start with the location 100. That means we have started to storing our instruction from location 100. That is your 100 location, 101, 102, 103 and so on. Okay. But here we have given the 1, 2, 3 for the sequence purpose only. Okay. First we will require to clear the E flag, then load the Y number into accumulator. For clearing E flag, we have instruction CLE. Loading the content from Y location to accumulator, we have instruction LDA. After this loading, we have to do circular shifting. For the circular shifting, we have instruction CIR. We are doing this circular shifting, right? For this, we have instruction CIR. And after this shifting, we will store this shifted version to the to the Y location by using this instruction STAY. Up to now, we have circular shifted right for checking the bit whether it is 1 or 0, and then store this shifted version to location Y. After this, we have to check for the E flag, okay, whether it is 1 or 0. For this, we can use this instruction like this instruction will skip this next instruction, that is branching to 1 instruction if E flag is 0. Okay, if your E flag is 0, that means you have to directly jump, you have to skip this instruction and directly jump to next instruction. Okay, if it is not 0, then it will branch to 1. Okay. And if it is 0, then it will go to this instruction, and here we have used this location branch to 0. We will use this 1 and 0 as a label in next instructions. After this, we have this 1 label. In this, we are going to, if your E flag is 1, then you have to add this shifted version and clear the E flag. If it is 0, then you have to do the just circular shifting. In 1 also you have to do the circular shifting. So first we will check for this portion that you have to require to do only when your E flag is 1. In this you have to load this number X, then add this number into P location and then store at P location. So that load the number X, then add the P location and then store at P location. And after that clear the E flag. Clear the E flag. This is the task if your carry flag or E flag is 1. If it is 0, or after shifting, after adding, you have to do this shifting. So after this we will use this 0 label. Okay, after this we will use this 0 label and then if we will load this number another time in accumulator, then we will do circular left shifting so that you can add this shifted left version in next time. Okay. For that we have to use CIL instruction and then store that shifted version into X location. So here we will use this LDAX instruction for loading, CIL instruction for circular left shifting and STAX instruction for storing that's contained to the X location. After completing this, you have to check for the CTR. If it is 0, then your task is completed. If it is not, then you have to jump to the some another location, and that location is up to clear E. That means you have to jump over here if it is not 0. Okay. First we have checked the E flag. If it is 0, then this instruction will be skipped. That is, your branching to the 1 will be skipped and directly it will go to next instruction, and that is branching to 0. So after that control will be over here, and if it is 1, then it will go to next instruction. That means it will go over here, and then after this all instructions are executed. Okay. After this we have to check for the CTR. So let me see how we can check for the CTR. In this, we will use the instruction ISZCTR. In this instruction, your CTR's content is going to be incremented by 1 first, and then it is going to be checked whether incremented content is 0 or not. If it is 0, then next instruction that you have used branching to loop is going to be skipped. If your content is 0, then your BUN instruction will be skipped. Otherwise, it will execute this instruction. That means it will branch to the loop. Whole task will be done second time, third time, fourth time, fifth time. When it is 0, then this instruction is skipped and directly it will jump to HLD. That means your code is completed. So by this way we can use this multiplication of these two positive numbers. Next we will see the same multiplication code by using some addition, or you can say repetitive addition method. For example, if you want to do 5 multiplied by 4, that means you are adding 5 4 times, that is 5 plus 5 plus 5 plus 5 4 times, that is equals to 4 multiplied by 5. Okay, by this method also you can do this multiplication program. So let me see how we can do this program. First we will start with the location 100, then we will load the number from location X to the accumulator. After that we will store that to the PTR location, so that our first number, first address of operand we have over here, first number, and then we are storing it to location PTR. After that we will load the second number, that is -4. Here if you want to do the 5 multiplied by 4, you will use one number as a pointer, and that pointer will be in terms of minus. That means if you are doing the operation 4 multiplied by 5, then you have to use 4 as a pointer or 5 as a counter, and at whichever number you use as a counter you have to store as a minus. So we are using this 4 as a counter, so we will store it as an NBR by means of minus, or you can say by means of negative number. So we will store -4, and that is going to be used as a pointer, and we will increment it by 1. And after that we will store this to the location STAY, or by using this STAY instruction we will store it to the location Y, where we have already 0, or you can say which location we have already cleared. After this we will clear the accumulator, so that our partial addition can be started. Then we have to use this instruction called as a add PTRI. Here we have used the indirect addressing. Okay, we are adding this number by means of indirect addressing. In this instruction, your location PTR is first going to be used, where we have stored your location, where you have stored your data, and after that you are going to adding this by using I. That is, it will go first PTR location, find out the content of that PTR location, and that will be used as an address, and from that address your content is going to be stored. Okay, that is your file, that will be your file number, and that is going to be added into the accumulator, that is you have already cleared. And after this addition you have to increment this y, that is your counter. Okay, and after, if you can use this instruction ISZY. If your counter is not 0, then you have to branch to the loop. If your counter is 0, then next to next instruction, after VU and whatever instruction we will write, that is going to be executed. So after that we will use this STA instruction. After completing this loop, your multiplication result is going to be stored into accumulator, and that you have to store at MUL location. We will use the instruction STA MUL, that we have 0. Okay, so after this you can store this into MUL location and then HLT instruction to end this program, or you can say complete this program. So here we have first loaded the number location of the first number and then stored at the pointer location, then loaded the second number as a pointer and then store at a Y location, which we will use as a counter. Then clear the accumulator and do the addition operation by indirect addressing up to when your counter is not 0, and after addition store this result to the MUL location. Okay, so by this way we can do this multiplication of this two positive number, okay, by means of repetitive addition. So here we are ending our today's session. If you have any query, then you can contact me.